Hello viewers, welcome back to the lecture number 17. So today we are going to discuss the lecture 17. So in the previous lecture we have discussed that how we can apply the Newton-Raphson method for solving a system of equation. So today we will do the example based on that one, and then we will do the MATLAB coding. So let us do one example here using the Newton method for system. So we are talking about here the two dimensional system, like suppose I have fxy. So this one I will take the equation x square plus y square minus y minus 5, and another function I have. So this is y minus e minus x minus 1. So I have now two equation, that is a function of two variable x and y, and I want to find the roots of this equation. So this is the case 1 I can take. So this will solve using the MATLAB code. Now I take the case 2, that how we can find the complex root. So suppose I have a function in z that is equal to 0, where z is a complex number x plus iy. So in this case let us take the example that suppose my fz is, I am taking z cube minus 3z plus 52, and I want to find what is my fz is equal to 0. So this z I want to find. So suppose z naught is equal to x naught plus iy naught is the root, is a root of this equation. So you know that this is in the complex form, and in fact this is an analytical function. So I can split this function as a function of x plus iy. So this z is there. So I should write this as the capital F. So it is capital F, capital F. Now I can put x plus iy, just substituting the x plus iy plus 52. Then I can expand this one. So it will be x cube plus iy cube plus 3x square iy plus 3x iy square minus 3x minus 3iy plus 52. So this one I can write like this. This one I can expand. So I cube, you know that I square is 1 and minus I cube is minus I. So sorry, I cube is I, because I is minus 1 under the root. So that we already know. So from here I can write this will be equal to plus I cube y cube plus 3x square yi plus 3x. So I square will be 1, so it will be y square minus 3x minus 3iy plus 52. Now I can expand, and I can collect the real terms and the imaginary terms. So I can write here the x cube minus 3x y square. So this is, sorry, this is minus 1. I have written here it is minus 1, and then it will be I cube will be minus I. So that is what I wanted to do. Okay. So this is, from here I can write this as minus. So I can write from here minus 3x y square. So this one is okay. Then I can write here from here minus 3x and plus 52. So, this is the real part I can take, because here I am iota, 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 and from here I can write that imaginary part will be 3x. So, this is I have taken 3x square y. So, this one is I have taken minus y cube, because this will be minus iota. So, this is the I cube, and minus 3y. So, that will be the real part and the imaginary part. So, from here I can write my fz is equal to this. Now, from here I can write that my fz is equal to, that is a function of x and y plus I times another function of x and y. So, I can take g as a function of x and y. Now, if I am able to find the value of x and y such that my f x y is equal to 0 and g of x y is equal to 0. So, based on this one I can find that my f of z will be 0. So, that will be the root of this equation when in the complex form. So, then we can say, so whatever the value of x and y I am getting from here, I can write that z is equal to that x naught plus I naught is a root of equation number, I can take this equation number 1. So, by this way we can find the root of the equation. So, let us go to the MATLAB code. So, let us MATLAB code. So, today, so let us start with the MATLAB code. So, today I have already made the code for you, because now we are familiar that how to write a code. So, let us start with the code I have made. So, this is the code I have started with. So, that is the function value. So, this is the function, and it gives you the x and iteration. Now, I keep the name Newton system. So, this capital F is the function, that is whatever we are going to define. J is the Jacobian, that we already know that how to, because in this case I have to find the Jacobian also, where x is the vector now, which has the two component x and y. So, x1 is x and x2 is y, and this is the tolerance we are giving. So, this program solve nonlinear system f equal to 0 by Newton method. J is the Jacobian. Jacobian we know that it is a partial derivative with respect to the variable x and y. So, that is the Jacobian. So, this is my x I have written, that x is x1 and x2, and that x is equal to x naught is the starting value, the initial value what we are going to start with. So, now from here I write that f x, so whatever the function I am getting, I put the value of x and I get the value of f y, f value. Then in this case, because it is a vector valued function, so we have to find the norm of that one. Instead of absolute value, we are finding the norm. So, L2 norm if we take, so this will be the L2 norm. So, that will be the norm. Now, we start with here with the iteration starting from the 0. Now, from here I know that how to write the f print f is initial approximation of x and y. So, that value I gives here. So, this is the value of x1 and this is the value of x2. So, this value is I am getting from this vector. So, this will be displayed as a x1 means the component of x at the first position and the component of the x at the second position. So, this will be displayed here. Now, I will start with the same, the while loop. So, whenever the f norm is greater than tolerance and iteration is less than 100. So, this is the AND condition. So, both should be satisfied. If any one of the condition is not satisfied, then this will not the while loop will not compile or it will not work. So, from here I see that the f norm is greater than tolerance and iteration is also less than 100. So, this is true. Then I will go to the delta. So, delta is what? The Jacobian. So, because in the previous you have seen that you will get a system of equation like this one. So, I will get from here the J delta is equal to minus of f values. So, this is we are going to get. So, J is the Jacobian, then this is the value I was going to find out. Basically, this was giving you the approximation of the roots x and y, and that was equal to the value of the function minus value of the function. So, now from here if I want to find delta, so what I do? I have to find the inverse of J and then multiply by the whatever the value we are going to write here. So, this is, so I am going to find this value. So, in MATLAB instead of finding the inverse we have a backslash information. So, this is the backslash we are going to use. So, in this case f value is the value of the function. So, this is the Jacobian and this is the backslash. So, backslash is the inverse, basically left inverse, because it is the backslash. So, it is going to give you the left inverse. So, Jx and the value of the function. So, it is going to solve the system J delta is equal to minus f value. So, from here this system will be solved and I will get the value of delta. Now, I will put the value of delta in the initial approximation and my approximation x will be improved, and then I will find the value of f, because this is the function we are passing. So, whatever the new x I am getting here, I will get the value of the function here. So, that is the f value, and the same one it is the norm of that function. Now, I will find the iteration, increase the iteration by 1, and then I will making the print of that one, that what is the root of this, finding the root at each iteration. So, this will be written here and then it will be the end of this while loop. And now, if it is here that here either a solution is found or too many iteration. So, if f norm is greater than tolerance, iteration will be minus 1 and then this is the end of the function. So, this function I have started with the name Newton underscore system. So, this name and the file name will be same. So, this is my function we are calling. Now, I have to write the main program. So, the main program is written like this. So, here because we are dealing with the system of equations, so I am writing this function in the form of a function value. So, I am writing function test Newton system and no argument. It means it will work as a script file. So, in this case I will start with the name of this function, that is test Newton system. So, I will start with the CLC whatever is written there. Then I will give the expected value, expected root. So, whatever the root I am going to expect, so I will write here. Then I will pass the tolerance, and then this is the function I am calling from here, the Newton system, whatever just we have defined. So, this is the function I am passing at the rate. So, unanimous function I am passing. So, this is the f, that is the Jacobian. This is the initial approximation, that was the x here, and that is the tolerance we are passing. And then error I am finding the norm. So, norm means L2 norm, expected value whatever the root is there minus whatever the approximation we are getting. So, I am finding that error, and here I am printing the error. So, this is function we are finding here. Now, what I am doing is that I have to define what is my f and what is my Jacobian. So, in this case I am calling within this function, I am defining another function f, that is f vector is equal to fx. So, here I will give the value of x and I will find the value of f. So, from here if you give me the value of x, it will give you the value of the f at that x. So, now I will start with my case 1 and case 2. So, let us start with, so I will just starting with the case 1. So, this is I am going to start with. Now, my expected value will be 2.22 and 1.11 for the test case 1. So, whatever the test case 1 I have taken. Okay. So, in this case I am starting with the initial value 1 and tolerance I am taking 10 raised to power minus 4. Now, I will start with the function. So, my function was x square plus y square minus y minus 5. So, I am writing a function that is a vector valued. So, x1 square plus x2 square, x2 means the y. Basically, this is the second component of the vector x, and that is basically whatever we have written in is a y value. So, this is the x value, this is the y value, minus y minus 5. So, that is the first value of the vector, and the second value is, here I am writing the semicolon, means I am writing a column vector, and this 3 dots are that if the vector is, if the value of the function is very large, then sometime we have to write the value in the next in the line. So, for the continue of the line we put the 3 dots. So, it means that the next line will be the continue of this one. So, this is my first function, and the second function gxy was y minus, so y minus exponential minus x minus 1. So, that is the function value we have defined. So, we have defined a column vector with the fxy here and gxy here. Now, this is the first function we have defined. Now, I have defined the Jacobian. So, J matrix I am defining. So, from here I am taking the value of x. So, Jx will be defined here. So, J matrix is equal to Jx. So, J matrix will be what? I am taking the partial derivative of this function. So, x square. So, let us from here. So, I am taking the Jacobian now. So, Jacobian basically is this one. So, that is my fx, fy, gx, gy. So, this is the Jacobian we are going to find from here. So, now from here I have defined my fx. So, fx is 2x, fy will be 2y minus 1, gx will be e raised to power minus x, because it will be minus 1. So, minus 1 will go out. So, and my gy will be 1. So, that is the Jacobian. So, from here I will find my Jacobian 2x, 2y minus 1, e raised to power minus x and 1. So, that will be my Jacobian I am going to pass for this function. So, this is my Jx, and f vector I have defined like this one, f xy and g xy, and this x in the code I have defining is a vector. So, x1 and x2. So, basically this is my x and this is my y, because in the MATLAB code we have to define the multi-valued vector in this form, or multi-valued variable in this form x and y in the vector form. So, that we are going to define. The same way for this function, now I will define my fz. So, my fx and gx y will be this one. So, based on this one I will find the Jacobian. So, Jacobian will be, so again fx. So, I will find the partial derivative of this function with respect to x. So, this would be 3x square minus 3y square minus 3. With respect to y, so it will be minus 6xy, that is it. From here I will find the with respect to x. So, it will be 6xy, and with respect to y it will be 3x square minus 3y square minus 3. So, that will be my Jacobian here, and my vector will be f x y, and gxy. Okay. So, this is the way we have defined. So, let us write my jx here. So, now my jx is defined. So, in the as in the previous one we have defined the jx. So, jx was, so it was 2x then 2y minus 1 e raised to power minus x and 1. So, that is my Jacobian. So, now from here I will get the value of x. From here I will pass the value of f vector. So, f vector is equal to f x and j matrix is equal to j x, and these vectors, these values of the vectors will be passed to this function. So, at the rate f and at the rate j means this is the function value. Now, let us run this one. So, let us so there is some and term. So, this is we have to write function and then function and. This is a test case, this one. So, we have to write like this one. Now, I will find the value of the function. So, this is the, so I started with 1 1 and after 5 iteration that is my solution. So, it is 2.20 and 1.10 and my error L2 error is giving, is finding here 0.011. So, this is the value we are getting, because here the expected value is also not known, it is just the approximation value of the roots. So, that is why whatever the value we are getting is the value corresponding to the error corresponding to this expected value. Now, we can even change the initial condition and then let us run this one. So, in this case you can see that even with the 3 iteration we are getting the solution and the error is this one. So, based on that whatever the value you are going to take, let us see with the 0 1. So, see in this case we have to take 8 iteration and the results are giving you the different roots. So, it is giving you the x is equal to this value and y is equal to this value. So, in this case my root is not getting the same one, because you have to tell in the initial that around which you are going to find the root. So, in this case I am going to find the root near to 2.22 and 1.11. So, that is why I have to start with this value, or maybe I can start with 1.5 and then let us see what will happen. Now, we are adding converging to this root. So, it is based on that which roots you want, because it may have more than one root and you do not know that which roots you are going to find. So, in this case I am going to find the root here. So, I take this initial condition and based on this initial condition my root is converging to 2.20 and 1.10. So, this is what we expected. So, that is the way we can solve the test case 1. Now, I will do the test case 2. So, I will comment this one and I will start with this. So, let us do the test case 2. So, in this case I will change my expected value. So, in this case the complex functions whatever we have defined. So, this is the function we have defined, f vector is x1's cube minus 3x1 y square minus 3x plus 52. So, that was my fxy, and the second was 3 plus 3x1, x1 means x. So, 3x square into y minus y cube minus 3y. So, that was my gxy, the another function, and the Jacobian we have defined. So, that is the fx value, this is fy value, and this is my gx value and this is my gy value. So, based on this one I am giving you the Jacobian. So, Jacobian we are getting, and I am expecting this value as a 2 3 as the root of this one. So, we will start with this same initial condition and I run this one and let us see. So, based on this one initial approximation 1 1, after the 7th iteration we are getting my root 2 3, and because in this case we already know that the exact value of the root, that is 2 and 3. So, you can see that L2 error is very small, 10 raised to the power minus 12. So, in this case my root is, I am almost after 7 iteration our root is very close to the exact value, it is converging very fast. So, maybe I can take some another condition, maybe I start with 0 and 1 and let us see whether we are heading toward the same root or the different root. So, from here you can see that we started with this one, and in this case the iteration are large 13, but after the 13 iterations I am heading toward the root. So, this is the approximation of the root, and L2 error is 10 raised to the power minus 8, 8 into 10 raised to the power minus 8. So, that is the value of the root of the function f z equal to 0. Even may I can change this value and I can take this initial approximation. So, based on this one, no, so that is a not defined function there. So, we cannot give the value 0 here. So, maybe I should give it 0.5 and let us see. No, it is okay, and after taking this value my iteration is, after 8 iteration I am getting this value. So, by this way I can solve the different equation, or maybe this is for 2 dimensional we have taken. Similarly, we can define for 3 dimensional. So, in that case my function here, this column vector will be another. So, this is the first vector, first value, second value, the third value we can define, and the same way the Jacobian will be changed, because if I take three functions, then the size of this Jacobian by 3 by 3 matrix. So, in this way we can find the roots of a system of equation. It may be 2 dimensional, 3 dimension, using the Newton system method. So, we just have to change the value of the function here, and based on this program you can find the root of the equation. So, this is we are able to find the root of the equation using the Newton-Raphson method for the system of equation. So, that is the end of this unit. From the next lecture we are going to start with another unit, that is how to deal with the linear systems and eigenvalue problems. So, thanks for watching this lecture. Thanks very much.